one thing I thought I would show you is just what astronomy looks like before you had photographs of the plates.
Sure.
So one of these books is actually a Project PHaEDRA book, so I thought you might be interested.
Sure.
It is an 1849 research journal, and
Okay.
I'll open it up to a page so you can see what exactly they were looking at. So in that time, we had the Great Refractor. It was the telescope that was the biggest in the world, along with its twin in Russia. They were both the biggest, so about 15-inch. So what they were looking at is Jupiter. So in this book, you have all of these handwritten notes. You also have drawings of Jupiter, because before you had photography, you had to rely on what people could draw in order to do their observations.
So to be a scientist, you had to be a little bit of an artist.
You did.
And
yeah.
precise. Okay.
So now we could look at this notebook and say, this is like a great relic of science, but it's also a great relic of art.
Okay.
So it's just a very interesting comparison to show this and then also a glass plate that shows Jupiter. So what I'm going to do, I actually have one here. So this is a glass plate of Jupiter from 1888. These are drawings of Jupiter from 1849, and you can see the difference, and this is a good page because there are two drawings of Jupiter, and of course they're very different because it's really difficult to make an exact drawing over and over and over again. And on every page, they're all a little different, so I could show you more of them as we go.
Okay.
But here we have a glass plate. It's kind of coming on. It's a multiple exposure.
Oh, all right, because that's why it has 5.
Yeah, so it has 5 images of Jupiter, but they're exactly the same. Every single one of them is exactly the same as photographs were.
And they were taken the same night?
Yep, the same night. Yep.
Why did they take 5?
That's a good question. A lot of our planet plates are multiple exposures, and I don't know if they were trying to save on glass. I'm not entirely sure. But I will open up a great page here that one of my favorites, and the binding on this book is pretty much gone.
Yeah.
But let me show you here.
Oh, wow.
I think this may have been someone else's favorite page because it looks like at one point in time someone spilled some tea on it. But we have 1, 2, 3, 4 drawings, possibly 5 drawings of Jupiter, and then we have 5 exposures of Jupiter.
How could they see that tiny, tiny, I mean, is that the size it looked to their eye when they put their eye up? And then
there are what we call loops like this,
or
even a very old magnifying glass.
So you're a detective.
Yes, kind of a star detective.
Cool.
To look at your glass plate. So it's just a lovely example of before photography, after photography, and it didn't just change how astronomy was studied back in those days, but also who could do astronomy back then. And that was because the women computers who worked here did not use the telescopes at night. It was considered improper at the time, but they were allowed to study these glass plates during the daytime and make amazing discoveries doing it that way. So using photography really opened up the world of science for other people.
Excellent.
So one thing that's interesting about this collection, I mean, there are several. First off, we have over 500,000 glass plates of the sky at both northern and southern hemispheres.
Right.
But the other part of this collection that I personally find very interesting is the fact that we had a whole team of women who were working here in the 1800s and 1900s who were studying the sky in a time when women really didn't have the opportunities that they have today to study astronomy or any science.
Right.
So they are collectively known as the women computers, which if you're transcribing for PHaEDRA, you might be familiar because a lot of you are transcribing their research notes from the late 1800s and early 1900s. So what I wanted to do is show you what some of their glass plates look like, because what you're transcribing through PHaEDRA are their notes, and you're seeing all those plate numbers, but if you haven't seen what an actual plate looks like, it would be good to connect the two.
Sure.
So I think what we could do is start off with Henrietta Leavitt, because we have some really interesting artifacts from her. So this is one of her glass plates. It's B20650, and it's one of my personal favorite glass plates for a couple of reasons.
Okay.
It was taken in 1897. And you'll notice a couple things about this plate. One, it has this tape around the edges, and it's a little bit thicker than other plates, and that's because there's this crack running through it. So at some point in time, someone may have dropped the plate or did something to the plate where it broke. And a lot of people ask us, what happens if you break a glass plate? Do you just throw it away? No, we do not throw them away. We mend them by using a method of archival tape around the edges and another piece of glass to stabilize the pieces.
Okay.
So that's one thing about this plate that I love. Another is down here, these markings, we believe are Henrietta Leavitt's. And that's because she had a very particular way of doing her research. But this up here, there are at least 2, if not 3 other types of handwriting from other people who were using this plate, and we
Excellent.
have no idea who they are.
Okay.
But hopefully, with the Project PHaEDRA transcriptions, we will someday know who all of the people were who were using this plate, because you are transcribing those plate numbers along with the research notes.
Sure.
So what I would like to show you is down here. So you see, typical of Henrietta Leavitt's work, she has letters. So she would point to specific dots or stars on this plate,
Right.
and then we would go to her notebook over here. So I'm going to take a little trip.
Okay.
So this is one of her notebooks. It's for the Large Magellanic Cloud, HSL right there. Those are her initials.
Sure.
So let's just open to a page.
Oh,
Here we
another
go.
delicate one. Okay.
Yes.
So that's why we take photos of them.
Exactly.
Okay.
So we don't have to use them as often if they're photographs.
Yep.
So this particular night or day that she was doing her research was actually November 3rd, 1906. She was very organized in her research. Up here we have different letters and numbers. Those are the plate numbers. So we have some more A plates, A2969, A2172, and underneath you see columns of letters, like what you saw on that glass plate. So these are the same stars on every plate. So what she would do is she would have identified these stars that vary over time. These variable stars would take a couple days to a couple weeks to go from their dimmest point to their brightest point to their dimmest point again, and she was trying to track that. So
that means basically the dot, it's getting smaller and bigger.
Yep, it's getting bigger and smaller over time. So what she would do is she would give those stars a letter, and she would look at different plates from different dates, and then she would measure how bright that dot on that plate is, using usually a magnifying glass or a loupe.
Okay.
But she also had another tool which we tend to really like. It's called a fly spanker, and we have a couple different sizes over here. Essentially what it is, it's a piece of a plate that has different size or different brightness of stars on them, and then they would write different numbers, which were the magnitude of that star. So if you were going to measure tiny dots all day, over and over and over again, you wouldn't want to just look at it with your eye and just guess. You would want a standard. So these fly spankers are your standard. So if you were going to measure, we'll just go over to our plate over here, and I'll put this one down.
Okay.
Just use this one. If you were going to measure this star A right here, you would hold this guy up to it and try and match that star to the size of the stars on your fly spanker, and then that would give you the magnitude of that star. So it was an easier way of measuring how bright stars are over and over and over again, which sounds very tedious, and I'm sure it was, but profound discoveries came from doing this. She essentially came up, the Leavitt law is named after her, also known as the period luminosity relationship. It gave astronomers a way to tell distance in space that they did not have before Henrietta Leavitt did this type of work.
Right.
So this is an example of the type of work Henrietta Leavitt did in her notebooks, which you are probably transcribing or have transcribed.
Light that gets
It would look
collected,
to your
right?
eye. It would look like it's changing.
It would look a little bit bigger.
Yeah.
Oh, okay.
I mean, you can't tell if you're looking throughout a night, like
Right.
you're doing stargazing, and
Okay.
the changes are often subtle,
Right.
more subtle than that. But
All
if you're
right.
looking at the same star over time,
Right.
and that's actually a reason that we're digitizing all of these plates, is because there's a lot of astronomers who are interested in looking at how different objects in the sky have changed over time.
Sure.
And you can only do that by looking at photographs of that night and many nights prior.
Sure.
Okay. So some of the other women who left research notes include Wilhelmina Fleming, Cecilia Payne-Kapashkin. I'm pretty sure people have been transcribing her notes. Antonia Mori, I'm not sure if we have notebooks from her.
I don't think we've started transcribing them yet, if we do.
But you might in the future.
Yeah.
So they all worked on what are known as spectra plates, and they look very different from the plates you've already seen. So I will show you a couple of them just so you can see. This one is a spectra plate, and it's focusing on two stars that are very close together. And it looks really wild if you've never seen one. This plate, I believe, is from 1888. So this spectra, what you would do is you have a telescope, like this photo of a telescope that I have here.
Mm-hmm.
You would put a prism in it. So I'm sure you've all seen when you have a prism held up to the sunlight, you get a nice little rainbow pattern.
Yes.
That's essentially what we're looking at here, except back then photography was in black and white, so you don't have the colors here. So they're not actually looking at the colors of this spectra, at least at this point in time. What they're looking at are these lines that are running through, and you'll get a nice close-up in a little bit so you can see what I'm talking about.
Sure.
And depending upon that pattern, they were making different discoveries. For example, Annie Jump Cannon was classifying stars based on those absorption lines that were running through, and what they realized was classifying stars based on their heat signatures. Women like Cecilia Payne-Gaposchkin, she discovered basically the chemical compositions of stars by looking at these sorts of things. And the funny thing is that for a long time, they didn't know what they were looking at. They just knew because these stars all look different, it meant something. And in order to crack that code, you have to find patterns, and you have to spend years looking at them in order to figure out what they mean.
Sure.
And just to give you another example of a spectra plate, this one is from 1914, and we know Annie Jump Cannon used this one.
Okay.
So her spectra that she looked at were not nearly as detailed as the ones that Cecilia Payne-Gaposchkin looked at, or Antonia Mori. Hers, she looked at a whole field of them, a whole star field. So instead of having one really big spectra, she has sometimes, it can go up to over 100 or hundreds of them on one plate.
Okay.
So what she would be looking at is only the really defined absorption lines that were running through. So depending upon what you were doing with this research, you would want more detail, or maybe you didn't need as much detail.
All right, and so this is how she was able to classify 300,000 stars.
Yes.
She didn't do them all. And then I think I heard she had they had a processing line going to be most efficient when using her time.
She was known to be extremely efficient. So in order to get the way she got 300,000 stars classified in her time here, she had a partner who would work with her, who would go over a plate, just like this one actually, and number. You can see this plate is filled with numbers. All the spectra have a different number. And then they would hand it over to Annie Jump Cannon, who would take her loupe or her magnifying glass, and she had memorized the different patterns that she was looking for. And so she would call out, number 37 is O, or number 46 is K. And then, so her notebooks are often lists, kind of similar to what Henrietta Leavitt's looks like, but a very different type of research was happening.
Sure.
Yeah, so that's how she was able to get through 300,000 in her time here.
Yeah, when I first started working here, I thought that's got to be a typo. That's just so phenomenal.
She's extremely efficient. So a lot of people compare the type of work that was happening here with these so-called women computers. I mean, today we would probably call them astronomers, but in that time they were known as computers. They had a very just efficient, almost factory-like operation going on here. They identified certain tasks for different people, and that is what they focused on. They did not deviate from that. It was extremely organized, and then they would publish every year what they had done.
Nice.
So that's how they manufactured so much data.